So if A is an m by n matrix with m rows and n columns, then the entry in the ith row and jth column is denoted by aij. So row first, then column. And it's called the ijth entry. So in some of your assessments, I saw you, like people were sort of writing it out longhand. There's a pivot in the second row and the third column. You'd say it like longhand in English. Now you have this aij and ijth entry vocabulary. It will make your life less miserable. Okay, and continuing on, we could call the entries going along kind of where the row and column match. We could call these the diagonal entries, and they form the main diagonal. Make sure you're tracking. These would be the ones right here. So then diagonals are really a big deal. So we're going to say something is a diagonal matrix. If it's square and whose non-diagonal entries are all 0. So here, this would be if we had it up above, but you had zeros everywhere else. If the diagonals were 0 as well, then you'd have a 0 matrix, which is not very exciting. Question?
I didn't get the top part. I was looking for my notes.
Oh, your 2-1 notes?
Yeah, sorry about that.
It's okay. So we already talked about it, but we have the identity matrix. And in the identity matrix, what entries are along the diagonal? Yay, happy ones. Okay. And then the very fun matrix that Sammy and Croy were talking about earlier that has all zeros, we're going to cleverly call, it's going to blow your mind, the 0 matrix. Okay. So notice that you now have 0, 0, and 0. So this one's a number. This one's a vector. And maybe this one, maybe we could put like a m by n. So this one's a matrix. So you could have 3 kinds of zeros. Not all zeros are created equal, which is a little bit strange to say. You could even have different 0 matrices because they would be different sizes. Come on. Come on. Okay. Cleverly enough, we will say that 2 matrices are equal if they are the same size, that is, have the same number of rows and columns, and the corresponding entries are equal. So what is slightly interesting about this definition is if you think back to your row reduction steps where you're like swapping rows or adding 2 rows together, what this tells you is that the matrices that you're creating, those were not equivalent matrices. They were the same size, but the entries were different. Okay, they back in that section we introduced the idea of a row equivalent. So they had the same solution set, but they weren't the same matrix. Here we're talking about matrices that are actually the same. So good morning. We're going to continue off in section 2.1 talking about matrix operations. And we would say that that the sum of two matrices like A plus B is the sum of their corresponding entries. Thus, two matrices can only be added if they're the same dimension. If their size or dimension, m by n, is the same. Otherwise, the sum isn't defined. So, for example, if you have your A's, which are here, and you want to add them to your B matrix, which is kind of pinkish, then all you're doing is you're taking the corresponding entries and adding them. So I'm taking the 2 here, and I'm adding it to the 1 there, giving me the 3 below. So just add corresponding entries. Probably exactly like you would expect it to happen. B plus C, what happens in B plus C? It's not defined, you can't do it. So we might say that you have mismatched dimensions. So the operation is undefined, like can't be done. Yep, for anyone that's a programmer that's had to work with lists or arrays, you've had this happen probably many times to you. Where, I mean, you'd think it's really obvious, like, wait, these things are the same size, you shouldn't be able to do it. But it happens all the time. Can we turn?
Yeah.
I'm looking at Ben's question. Yeah, we could certainly create a new C that would make the operation defined. Whether that would make sense or not kind of depends upon the application or the question we're trying to address. So let's see.
Professor, I didn't get the.
I'm gonna short version to add. Did I skip over? I'm good. Yeah, short version to add. Add matrices. You just add corresponding entries. I need 4. Where am I at? Something's weird in my notes. Oh, I skipped the page. That's what's wrong. All right. So that was if you add, that's pretty straightforward. So the scalar multiple, it's sort of like doing it with vectors that you've done in the past. RA is the matrix whose entries are R times each entry of A. And the matrix negative A represents -1 times A. And shockingly enough, A minus B is the same as A plus -B. Okay. So the point of all this is that addition, scalar multiplication, subtraction, all these things happen the way you would expect them to. So for example, if I wanted to find 2A given A, notice here I have 2, and I'm going to find 2 times A, and so 2 times 2 would be 4, or 2 times -2 would be -4. In part B, if I want to find B minus 2A, I could take my B matrix here, subtract out 2 times my A matrix, and just find the difference in the entries. So again, like 5 minus 6 put together give you the -1. So addition, subtraction, scalar multiplication happen just like you would expect them to happen. So theorem 1 is nice. It's basically saying that all these things work. So in A, we're saying that when you're adding, the order doesn't matter. In B, we're saying that you have associativity in addition. So you can associate, you could say, well, the A and the B work together, or the B and the C work together, works either way. In C, we're saying you can add a 0 in. What kind of 0 is this? This would be the 0 what? This would be the 0 matrix, not vector. So it's a 0 matrix. So thanks for that. I think that was Evan and Richard, Alex, and Croy. In D, you have the scalar. Now here you have your scalar R, and it can be distributed just like has happened in the past. In E, you can see, again, you take those scalars and we could distribute the scalars through. And in F, you have the associativity of the scalars. So nothing too complicated. Again, all of this stuff is intuitive. Is this a word that people know? Do people know this word? Yeah, so standard word, what does it mean? Simple, as expected, how it seems. Yeah, I like, those are all good. So it's something that we sort of look at, and it should just sort of, it's supposed to make sense to us. Sometimes in math, we can fall prey to saying things are obvious or saying things are intuitive that aren't intuitive or aren't obvious to everyone. Like that happens. And I know I've been on the receiving end of that when somebody said something is obvious and I'm like, it's not obvious to me. So I'm saying that this is intuitive. I recognize that it might not be intuitive to everyone. I'm happy to go into it more after class if people have questions. So now let's go talk about something that's a little bit stranger, which is matrix multiplication. So let me make sure that it's clear what's going on. All of these are scalar multiplication or some version of scalar multiplication. Whereas down below, here we're going to be talking about matrix multiplication. Like we talked a little bit about this before when we did a matrix times a vector. And so this is just building on that same concept. And so like with the matrix times a vector, where we had 2 representations, here again, we will have 2 representations. So one way of thinking about the matrix A times B is, let me do it this way. A times B is you take that first matrix A and leave it in place, and then take the second matrix B and write it in terms of its columns. And so to find A times B, you take the full matrix A and then multiply it by the first column. And that makes the first column of your result. Full matrix A times the second column of B, etc., all the way to the pth column of B. So here we're doing matrix times column. Kind of like at each entry. So for example, if I want to compute C times A, so notice in this case that the C is the one coming first. So if I want to find C times A, I'll take C and then I'll multiply it by each of those columns of A, right here, here, and here. Okay. And so to do this, we could find C times A1. So that would be 4, 3, 2, 1 times A1, which would be 2, negative 3. So here I'm taking the yellow C and I'm multiplying it by the first column of A. And that's going to equal, remember how you do this? You do row dotted with columns. So 4 times 2 is 8, minus 3 times negative 3, so minus 1. And then 2 times 2 minus 3 is 1. And so that will give me this result. Gives me that C times A equals minus 1, 1 from here. That gives me my first column. And then this, I already worked out the next two. So C times A2 is 5, 1. So that'll give me my second column. And then C times A3, negative 6, negative 2. And that'll give me my third column. Questions about that approach to matrix multiplication? Give me a thumbs up when you're ready to move on. What if A has more rows? If A has more rows, then it wouldn't be defined. So I think we're going to talk about that just next. So good question, Hui. Keep going. All right, so let's just talk about the dimension side of this. So this is sort of getting at Hui's question. So we want to ask, is the matrix C times A defined? So first of all, what are the dimensions of matrix A? So it's 2 by 3. Remember, it's rows, then columns. And then what are the dimensions of matrix C? Got a 2 by 2. And so remember, in order for this to work, the middle ones have to match. Okay. So this is another case, since 3 does not equal 2, at least on a Wednesday, this is another case where we would say that we have mismatched dimensions. I guess that most of you have taken chemistry or physics. And in chemistry and physics, sometimes you're taught to follow the units. Like you might not understand what you're doing, but you follow the units, and sometimes just following the units is enough to get you through a question. And here we follow the dimensions, and sometimes the dimensions are enough to get us where we're going. So from Ahmed, he said, so CA and AC are different results. Yeah, they're definitely different results. So you could think about it this way and say that that CA is defined, right, and AC is undefined. So it's not just that they have different results. One of them doesn't even make sense. Like one of them doesn't even work. So this is a place that is not intuitive. Matrix multiplication is not intuitive.
Dusty, wouldn't it work if we had for C 2 by 3?
2 by 3. If C was 3 by 2, it would work.
The dimensions wouldn't match, but it would be like just like A, so it wouldn't multiplication.
Oh, yeah, no. No, so if you have A, which is 2 by 3, times C, which is 2 by 3 as well, again, you're going to have mismatched dimensions, so it's not going to work. So you could say that the dimensions don't match. And when you're talking about the dimensions don't match, what you're talking about is the columns of A and the rows of C. Yeah. Which I think answers Ryan's question. Did that answer your question, Evan? Sometimes, so from Alex, so we can't multiply any matrices with the same dimension. Well, maybe, it depends. So if we had A that was 4 by 4 and B that was 4 by 4, then here they would match. So these guys have the same dimensions and it works. But the outer ones don't actually matter. Yeah. It's kind of strange. So let's talk about the other way of doing matrix multiplication, which would be the row column rule for computing AB. And this is what I was pushing you to earlier. So if the product AB is defined, then the entry in row I and column J of AB, like of the result, is the sum of the products of the corresponding entries from row I of A and column J of B. If ABIJ denotes the ijth entry of AB, then A is an n by n matrix, then, oh my gosh, that's an awful lot of writing. Let's do an example. So if I want to find the entries in the third row of AB, then what I'm going to here, then I'm going to, so I want the third row, I'm going to look at the third row of A and see how this all plays out. So I've got A times B. What are the dimensions of matrix A? Four by 3. Good. What are the dimensions of matrix B? 3 by 2. So it works. We have corresponding, we have dimensions that work. The dimensions of the result are going to be 4 by 2. Right there. That's going to be how our output works. And so to find the things in the third row, we're going to take, trying to get my colors right. We're going to take the yellow and dot it with the orange, and that'll give us this first entry. I don't know what color to use here. And then, so let's see that. So we'd have 6 times 4 plus negative 8 times 7 plus negative 7 times 3, which is what? Let me see if I can get the colors in there. 6. I got a negative 53 from Abed. Thank you. So we're going to get a negative 53 here. And then we'll take that same yellow row and now we'll multiply it by maybe the blue column. And that'll give us our second box. So we have same 6, negative 8, and negative 7. And we're going to multiply it by negative 6, 1, and 2. I've got some negative 58-ness is what I'm seeing in the chat. Thank you. Okay. So this would be the third row of AB. So when I'm doing this, if I was doing this on a whiteboard or I was doing it in, like I'm doing it on my paper, I don't like write out all that stuff. What I'm always doing is I'm going like this. I'm like row times column. And is this backwards to you or is this, am I in the correct order? Left to right? Or is that reversed? Is this your left or is this your right? Your right. Okay. So I have to go like that to make it look right. First matrix times matrix or row of the first matrix, column of the second matrix. And so I'll choose my row and I'll go column, 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 column. And that'll give me my first row of the next one. And I'll go to the second row, column, 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 column. And I'll go to the third row, column, 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 whatever it is. And each of those, what I'm doing is I'm doing a dot product. So I'm taking the first entries, multiplying them, second entries, multiplying them, third entries, multiplying them, and then adding all those things up. So it's like a dot product gives me the first entry. Dot product gives me my second entry. Dot product gives me my third entry. Next row. Dot product gives me a first entry. Something like that. And so like I'm literally just doing one of those weird moves. I can't do it. like it's like something like one of those moves. I'm literally just putting my hands on my paper or on the whiteboard or whatever it is to make it work. Don't try to be, you don't have to be smart. You don't have to impress people. Just get it right. If the matrices are really big, use your calculator because your calculator does really good math. If the matrices are small, it will take you longer to type them into your calculator than it would to actually just do this by hand. So kind of whatever works for you. Questions? Keep going. Cool. All right. So here's our next theorem. And you'll notice that some things work really nicely that associativity works, so you can associate the second two or the first two. You'll notice that in this next couple of lines, here and here, notice you have a left distributive law and a right distributive law, that the order matters. Pardon me. You'll notice that for scalar multiplication, it works just the way you would like it to work, that you can take that R and you can put the R in the front, you can put the R in the middle, you could put the R in the back. That's all fine and dandy. And you'll notice that the identity matrix works the way you would expect it to, with one slight difference. Notice here that A is a M by N matrix. M by N. And so you'll notice that on the front end, you have an IM if you multiply by I on the left, but you'll have an IN if you multiply by I on the right, because you have to make sure that the dimensions match. Questions about the theorem? So here's the big one. While the following properties are all true, be careful. The commutative property is not true. That is, AB does not, in general, equal BA. And I want to do an example of that. This is a big deal. It's not hard, but it's a big deal. Okay. So let's look at an example here. So again, I'm doing row times column. So first row times first column using dot products. I think I've got 1. First row times second column, 9 minus 5 minus 23. Did I do that? I feel like I did something wrong. Row times column. Oh no, that's right. Okay. And then it's a huge deal. So if you multiply the other direction, you'll say, so this, now we're looking at B times A. Let me make sure you're seeing it. Here's A times, here's A and here's B. So we're switching orders. And so minus 10, and you already can see that it's not going to work. 7, 14, and minus 12. Sometimes it will work. Like there's cases where it will work. Like if one of these matrices was 0, you could imagine that it would work. If one of them was the identity matrix, it could work. But in this case, it doesn't work. And like we saw previously, as you already pointed out, sometimes the multiplication doesn't even make sense in one of the directions because the dimensions work one direction but not the other. So in general, A times B does not equal B times A. So also the cancellation laws do not hold for matrix multiplication. Think about the number of things that you've done in algebra where you'd say, oh, I've got, you know, A times B equals A times C. And you're like, well, then that must mean that B equals C. Yeah, that's not going to hold up. It just doesn't work here. Let's see how that plays out in this example. So in 10, I want to verify that A times B equals AC, and yet B doesn't equal C. So here's my A's, here's my B and my C. Like in the old days, like if A times B equals A times C, then blue would equal green. So let's see what happens. So A times B, 16. We've got 1, 8 minus 15, 7, 32, minus 2, 16, plus 14. Okay. 1 equals 10 minus 1. So far, so good. Minus 7, minus 20. Minus 20 plus 27 is 7. Wait. 20 plus 18 is minus 2. And 8 plus 6 is 14. So notice here you have AB equals AC, but B does not equal C. So you all knew the word intuitive, or everybody seemed to be happy about that word. So we have a new word here, maybe one that you use a little less often. So we would say that this is counterintuitive. Or not intuitive. What happened to warnings 4 to 9? What happened to warnings 4 to 9? Oh, in the notes? Yeah, it's a special numbering system that's also counterintuitive. This is, it says here, exercise 10. This is exercise 10. Okay. So I just skipped over 3. And then I also want to do an example. The next example will be about number 3. So this next one is, says see exercise number 12. And so let's look at the 12 right here. That's the 12. Nice, Ahmed. Yeah. So here we have let A equal 3, -6, -1, 2. And I want to construct a 2 by 2 matrix B such that AB is the 0 matrix, but B is actually interesting. So there could be more than one answer here, but one answer would be A times B so I'm going to have a 2 by 2 matrix here, a 2 by 2 matrix here, and I want this to be equal to 0, 0, 0, 0, also a 2 by 2 matrix. And so the middle ones are going to match. The outside dimensions will give you the dimensions of your result. And so we're just going to make something up. And so maybe I'll try 2 and 1 here. So notice that 3 times 2 is 6, minus 6 times 1 is 0. And -1 times 2 is 2, plus 2 times 1 is 0. And then we could try 4 times 2, or 4 and 2 there, and the same thing works. So think about what we're just doing. Like in the old days, of yesterday, then you would have something like x plus 1 times x minus 2 equals 0. And if you had something times something equals 0, then you knew that either the first one, x plus 1 equals 0, or the second one equaled 0. That's what happened in the old days. But now, in our new world, in our brave new world, we have a times b equals 0, and yet a doesn't equal 0, and b doesn't equal to 0. Come on. Ah, sorry. Come on.
Dusty, so the way you find the matrix B was just guess what makes the final answer 0?
Yeah, in this case, I just did a little bit of guess and checking. Yep.
Alright.
Yep. So craziness. All right. Next thing we've got is pretty easy. So it's a little easier than this whole multiplication thing. And so we're going to define a new concept called, sorry, I don't want to lose track of one thing here. I almost lost it. So, sorry, I almost lost this one line. So if A is an n by n matrix, notice it's square. If k is a positive integer, then a to the k would be the same thing as a times a times a times a k times. Kind of like what you'd expect. Yeah. Okay. So let's talk a little bit about the transpose, which is not that difficult to understand. So if an m by n matrix A is given, then the transpose of A is an n by m. Let me make sure you're seeing the order here. This one's m by n. So notice that the order is reversing. The order is changing. And it's denoted by the notation A, and then you have looks like a power of t, but that means transpose, whose columns are formed by the corresponding rows of A. So there's a couple of different examples here, but let me just show you one of them. I think this is pretty straightforward. So if you're given this matrix C, notice that the first row of C becomes the first column of C transpose, and the second row of C becomes the second column of C transpose. Something like that. So just rows, you just swap rows and columns. I think it should be obvious that if you had C transpose and you transposed it again, that you would get back what you started with, right? It's like swap the row to a column and then the column back to a row. Okay. So a couple of theorems about that. Just like we said, if you transpose a transpose, you get back what you started. If you want to do this with addition, you just spread out the t's. That one's easy. If you have scalar multiplication, you don't do anything special with the scalar. You're just transposing the matrix. And the one here that's a little bit, you got to be a little bit careful with is this last one. So notice that the order changes. If you have a product, A times B transpose would be the same as B transpose times A transpose. And this is going to be important later. This will come up in chapter 6. At which point all of you will have already forgotten that we talked about this.